Okay, if we have an eigenvector basis B equal V1, V2, then any transformation relative to that basis will be represented by a diagonal matrix. So that, for example, if this is an eigenvector basis and AB is negative 2, 3, what does that mean? Negative 2, 3 with zeros in the opposite diagonal. Well, since x sub b, the representation of any vector in, say, R2 relative to this basis equal alpha beta relative to that basis means alpha times V1 plus beta times V2, this, and transformation matrix multiplied by alpha beta, and I'll put the subscripts here to be clear. If I multiply this matrix by this, it's clear that I get negative 2 alpha 3 beta. And what does that mean? That means negative 2 alpha V1 plus 3 alpha V2. I don't really need the equal sign there. Okay? So the transformation of alpha beta is the vector you get from the transformation. And I could say that would be the transformation of alpha beta relative to the matrix B equals negative 2 alpha V1 plus 3 alpha V2. Okay, what does this tell you about the transformation? Well, since alpha V1 gives you negative 2 alpha V1, that must mean that V1 was equal to negative 2 V1. The alpha is just a constant in a linear transformation. The constant just goes along for the ride. Okay, so this tells you that V1 transforms to negative 2 V1. Okay, and it also tells you that V2 transforms to 3 V2, meaning that V1 is an eigenvector with an eigenvalue negative 2, V2 is an eigenvector with an eigenvalue of 3. V1 being a vector that transforms to a vector of twice the length in the opposite direction, V2 being a vector that transforms to a vector of 3 times the length in the same direction. Okay, so now from this being equal to this, we conclude that V1 is negative 2V. V1 transforms to negative 2V1, V2 to 3 times V2. Okay, now in the standard basis, what does the transformation look like? Well, alpha V1 plus beta V2 equals alpha times, well, the V1 vector. Now, I didn't specify up here what these vectors were, so now let's go ahead and say that V1 is the vector negative 2, 1, and V2 the vector negative 4, negative 3. Okay, so now we can say that alpha V1 plus beta V2 means alpha times negative 2, 1 plus beta times negative 4, 3. And we can say that, well, that equals negative 2, 1, negative 4, 3, or this matrix multiplied by alpha beta. Again, our column of basis vectors matrix, and in this case, a column of eigenvectors basis. Since our transformation is represented by a diagonal matrix, that makes these eigenvectors. So we have this, and now the alpha beta is our representation of this vector with respect to this basis. Again, meaning alpha times this vector plus beta times this vector, because that's what we did, alpha times this vector plus beta times this vector. Okay, so if we multiply this out, of course, we're going to get, well, multiply it out and see what you get. You're going to get negative 2 alpha minus 4 beta, first row, alpha minus 3 beta in the second row, and those will be the coordinates that we have in our standard basis. Okay, so this matrix takes us from our basis here to our standard basis. The inverse of this matrix, being this, takes us from our standard basis to the basis B, basis we have here. I hesitated for a minute because I wasn't sure where the board went. Okay. We need to do this. Okay. We do a picture. Okay. What we want to find is we want to find the transformation relative to the standard basis. We know the transformation relative to the basis B, in this case an eigenvector basis. It doesn't matter whether this is an eigenvector basis or not. The only thing that makes this an eigenvector basis is the diagonal nature of this matrix. Okay, but if we have an eigenvector basis, then this matrix will have this form, and this will be the form of our transformation in that relative to that basis. Okay. Now, to go from the basis B to our standard basis, this is a matrix that we use. That's what I just said. You multiply this matrix by the basis B representation, and you get the form of the vector in the standard basis. You get the vector in R2, let's say. So, to go from basis B to standard basis, we multiply by this matrix. Okay? Now, if we want to go from the standard basis up to the basis B, which we don't want to do here, but we do want to do it here, we have to multiply by the inverse of this matrix. Okay? If we multiplied a vector here by this matrix, and then took what we got down here and multiplied it by the inverse matrix, it should be clear that we get the same thing we started with. So the inverse matrix takes us from the standard basis to the basis B. Okay, well then this tells us that the matrix A is what? Well, matrix A takes us from here to here. Okay, now if we start here, we can go this way, so the first thing we have to do to any vector down here is multiply it by this inverse matrix, so that's going to go here. And then to go from here to here, we multiply by the diagonal matrix. And then to go from here to here, we multiply by the column of eigenvectors matrix, or the column of basis vectors matrix. Okay, and now we have the matrix A. Now, we actually multiply this out and we get this. What we now know is that this matrix has to have the same eigenvectors that we have in B. In other words, that the eigenvectors of this matrix have to be -2, 1, and -4, -3. We also know that if we get that basis of eigenvectors, we can diagonalize this matrix. If we didn't know what this matrix came from, if we just had this matrix to start with, we could deduce its eigenvectors. We could do our column of eigenvectors matrix, and we could transform from here to here. We could figure out the transformation from here to here from our vector, from our matrix A. So knowing this matrix and knowing the two eigenvectors, we can figure out what our diagonal matrix would be. So if we verify this, we can start by finding the eigenvalues of this matrix. Okay, well, the eigenvalues are what? You take the determinant of this matrix minus lambda times the identity matrix. The determinant of the matrix 0 minus lambda, 4, 3/2, 1 minus lambda. We get this, which changes to this, which factors to this. Now this doesn't always factor, but for a 2 by 2 matrix you'll always get something you can solve, and if you get real solutions, you know you have real eigenvalues. And you can solve using the quadratic formula if you can't factor. Okay, in this case we could factor, and we immediately find that our eigenvalues are 3 and -2. Does that match? Well, yeah, we got -2 here, we got 3 here. Okay, so if we find our two eigenvectors that go with these two eigenvalues, we can form the column, and those eigenvectors had better be this one and this one. Okay, well, we'll go on with this.